Hi everyone, this is Kalyan Kumar and welcome to Chemistry Universe. In the last video we talked about resonance effect, and I also told you that resonance effect is actually the manifestation of the wave nature of electrons. And since we want to avoid doing a complicated molecular orbital approach, so we take the route of resonance effect, which bypasses the need to use the molecular orbital theory. But the actual theory that has to be used is the molecular orbital approach. So in this video, I'm going to give you a brief idea as to how the molecular orbital theory works for a conjugated pi bond systems where resonance occurs. And before that, I'm going to give you a brief idea about how we do it for a sigma bond, and then for a simple system like ethene, how it works for a pi bond, and then we'll go for the conjugated systems. So here we go, introduction to molecular orbital theory for pi bonds. And so before we do that, we'll start with the sigma bonds. Now the valence bond theory does a remarkably good job at explaining the bonding geometry of many of the functional groups in organic compounds. There are some areas, however, where the valence bond theory will fall short. It fails to adequately account, for example, for some interesting properties of compounds that contain alternating double and single bonds, the ones that show resonance. And in order to understand these properties, we need to think about chemical bonding in a new way, using the ideas of molecular orbital theory or MO approach. So let's go back and consider again the simplest possible covalent bond, the one in the molecular hydrogen. When we described the hydrogen molecule using valence bond theory, we said that two 1s orbitals from each atom overlap, allowing the two electrons to be shared and thus forming a covalent bond. In molecular orbital theory, we make a further statement. We say that the two atomic 1s orbitals mathematically combine to form two new orbitals. So basically what we're trying to say here is that we are going to consider the molecule like a single entity. Just like we considered an atom like a single entity with several energy levels, where we use the N+L rule, here we use the molecule, and in this case hydrogen molecule made up of two individual atoms. But once it forms a molecule, we'll say forget the two atoms. Treat the molecule as one single entity and treat it again in the form of energy levels. Put the electrons in various energy levels and do all your calculations based on that, and that should give you the same picture as you get using a valence bond theory, but in fact something better than that, because now we are also considering the wave nature of electrons. So recall that an atomic orbital such as the 1s orbital of a hydrogen atom describes a region of space around a single atom inside which electrons are likely to be found. A molecular orbital describes a region of space around two or more atoms inside which electrons are likely to be found. So this is in the case of a molecule. Mathematical principles tell us when orbitals combine, the number of orbitals before the combination takes place must be equal to the number of new orbitals that result from the combination of orbitals, and our orbitals just don't disappear. When two atomic 1s orbitals combine in the formation of H2, the result is two sigma orbitals. This is the energy axis. These are the individual 1s orbitals of the two hydrogen atoms. And as you can notice here, these are the nuclei of the two atoms, and this shaded region, this is the electron cloud. This is the electron cloud. So now let's see how it happens. We make these mathematically combined. These are individual atomic orbitals mathematically combined to form two molecular orbitals, one having energy lower than the two atomic orbitals, in which we can expect both electrons to be found, something like this, and this is called bonding. and the one having energy higher than these two, where there won't be any electrons, and they look like this. So as you can see, the region here has no electrons here, and we call this place as the nodal plane. This is called antibonding molecular orbitals, and this is called the nodal plane. Now, according to the MO theory, one sigma orbital is lower in energy than either of the two isolated atomic 1s orbitals. This lower sigma orbital is referred to as the bonding molecular orbital. The second sigma star orbital is higher in energy than the two atomic 1s orbitals and is referred to as the anti-bonding molecular orbital. The bonding sigma orbital, which holds both electrons on the ground state of the molecule, is egg-shaped, encompassing the two nuclei and with the highest likelihood of electrons being in the area between the two nuclei. The high energy anti-bonding sigma star orbitals can be visualized as a pair of droplets with areas of high electron density near both nuclei and a node, the area of zero electron density midway between the two nuclei. Remember that we are thinking here about an electron behaving as a wave. When two separate waves combine, they can do so with constructive interference, where the two amplitudes build up and reinforce each other, or destructive interference, where the two amplitudes cancel one another out. Now, the bonding MOs are the consequence of constructive interference between the two atomic orbitals, which results in an attractive interaction and an increase in electron density between the nuclei. The antibonding MOs are the consequence of destructive interference, which results in the repulsion interaction and a region of zero electron density between the nuclei. Following the same F-bow or the building up principle, which we learned in chemical bonding for writing out electronic configurations, we place the two electrons in the H2 molecule in the lowest energy molecular orbital, which is the bonding sigma orbital. The bonding attracting MO is full and the anti-bonding repelling MO is empty. So now let's figure this out for the ethene molecule. We are looking at the pi bonds now. I'm only going to show you the pi bonds and not the sigma bonds between the carbon atoms and the carbon and hydrogen atoms. So the advantage of using the MO theory to understand bonding in organic molecule becomes more apparent when we think of pi bond. Let's first consider the pi bond ethene from an MO theory standpoint, and in this example, as I said, I'll be disregarding the sigma bonds, the S bonds in the molecule, and thinking only about the pi bonds. We start with two atomic orbitals, one unhybridized 2p orbital from each carbon. Each contains a single electron, and in the MO theory, the two atomic orbitals combine mathematically to form two pi molecular orbitals, one in energy lower, which is the bonding, and the one energy higher, which is the anti-bond. So this is how I'm going to depict this. These are the individual, this is the energy axis. These are the individual orbitals, p orbitals. Now remember the blue and the red, there is no difference between them. These are basically the plus and the minus. And as far as the wave function is concerned, the plus and the minus have no difference as such. Okay, now when they combine, remember they can combine constructively, which means the blue and the blue meet, the red and the red meet. So you get one energy on top, one energy at the bottom. The bottom energy is where we expect the electrons to be, and it looks like this. The blue and the blue meet, the red and the red meet. So there is a bonding interaction in both blue and red, and this is called pi bonding MO. So remember, there is one bonding interaction here. Blue and red is taken as one bonding interaction. Now, but the blue could have met the red and the red could have met the blue. This gives rise to a nodal plane. So there is one anti-bonding interaction. So in the bonding pi orbital, the two blue lobes of the p orbitals interact constructively with each other, and as do the two red lobes. And remember, the color is arbitrarily chosen as for plus and minus. There is an increased electron density between the two carbon nuclei in the molecular orbital. It is the bonding interaction. In the high energy anti-bonding pi star, the blue lobe of one p orbital interacts destructively with the red lobe of the second p orbital, leading to a node between the two atoms and overall repulsion between the carbon. Again, using the building up principle, we place the two electrons in the lower energy and the higher energy antibonding remains empty. So now let's check this out for a molecule that typically shows resonance effect, because this is the molecule that we're interested in. So this is the molecule and these are the carbons, buta-1,3-diene, and there is a free rotation about the 2 and 3 carbon. From the valence bond theory, we expect C2 and C3 in this molecule to have a sigma bond and the rotation to be free. Experimentally, it is observed that there is a significant barrier to rotation about the C2-C3 bond and that the entire molecule is planar. In addition, the C2-C3 bond is 148 picometers long, which is shorter than a typical carbon-carbon single bond, 154, though longer than a typical carbon-carbon double bond, which is 134. So C2-C3 carbon have some pi interactions in them. The molecular orbital theory accounts for these observations with the concept of delocalized pi bonds. In this picture, the 4 2p atomic orbitals combine mathematically, again to form 4 pi molecular orbitals of increasing energy. 2 of these are called bonding, which are lower in energy than the p atomic orbitals from which they are formed, and 2 others are called anti-bonding, and they are higher in energy than the individual atomic orbitals. So let's have a look at this. This is going to be interesting. So energy axis, 4 orbitals having 1 electron each. Remember, these are the pi electrons, atomic orbitals, and this is the energy of atomic orbitals. So we have the bonding first. Psi1 is the wave function representing the molecular orbital here, and this is what it looks like. Now can you notice that the 4 atomic orbitals, they're all in bonding, they are in phase. The blues are meeting blues and the reds are meeting reds. So there is one bonding interaction here, one bonding interaction here, and one bonding interaction here. There are effectively 3 bonding interactions, and there are no nodes, so there are 0 antibonding interactions here. So 0 nodes, 3 bonding interactions, and 0 antibonding interactions. So net is 3 bonding. This is called the bonding MO. The next orbital of higher energy, here the pairs form bonding, but in between there is a node. See this node. The blues meet, the reds meet, but not all the 4 meet together. And as you can see, there is 1 bonding interaction here, 1 bonding interaction here, and 1 antibonding. So effectively 2 bonding and 1 antibonding, that makes it effectively 1 bonding. So it is still bonding. And there is 1 node. Then I have Psi3, which I have placed as antibonding, because here the net will be antibonding interaction. Look at this. You notice there are 2 nodes here. There is 1 antibonding interaction, 1 antibonding interaction, 1 bonding interaction. So what is the net? Net is 1 antibonding interaction. So 2 nodes here, 2 nodes, 1 bonding interaction, 2 antibonding interaction. Next net is 1 antibonding interaction. So this is called an antibonding MO. And the topmost, there is no bonding at all. Everything is out of phase. So node 1, node 2, node 3, 0 bonding and 3 antibonding. So the net is 3 antibonding. And if I have to fill the 4 electrons, remember FO principle, start from the lowest. So I'll fill 2 electrons here, 2 electrons here, which means in the actual molecule there is some pi interaction between the C2 and the C3 carbon, which the valence bond theory does not tell you, and for which we need to use the so-called resonance effect. The Psi2 is the highest occupied molecular orbital, it's called the HOMO, and the Psi3 star is the lowest unoccupied molecular orbital, it's called the LUMO. And of course, we'll talk about this a little bit in detail later. The lowest energy molecular orbital, Psi1, has only constructive interaction, and 0 nodes, higher in energy but still lower than the isolated P is the Psi 2, which has 1 node. And I think we discussed this in detail. Further, it's still bonding, and Psi 3 star and Psi 4 star have totally net antibonding, and by the above principle we fill the 4 electrons. Because Psi 1 includes constructive between C2 and C3, as I said, there is a degree in 1,3-butadiene molecule of pi bonding interaction between these two atoms. But remember, this double bond character is more between C1, C2 and C3, C4, because remember, in both MOs, the Psi 1 and Psi 2, there was pi bonding between C1, C2 and C3, C4. The valence bond picture of 1,3-butadiene shows the 2 pi bonds as being isolated, whereas here they are not, they are spread out. The molecular orbital theory gives you that the 4 pi electrons are actually spread out throughout the system. And it is this approach which is circumvented by using the hypothetical concept of resonance, because it is not possible to predict the nature of interaction of atomic orbitals to form bonding and antibonding modes that easily. Now, as you saw in this, I gave you a brief idea about the MO of resonating molecules. It's not always possible to do that, especially when there are different types of atoms involved. Here all of them were carbons, relatively simple, because all the carbons were similar, they all had the same energy, and that is what is possible to do a little bit of MO qualitative, even though MO by its very nature is actually quantitative. So that was basically to give you an idea about why we use resonance effect, which ultimately gives us the same idea as what we would have got had we used the MO approach, which of course is complicated. So with that, we come to the end of this video. I hope you were able to gain something from this video, and this video helped you in understanding the MO theory. You can of course avoid this video because you don't need this kind of an MO theory for the kind of exams you might be preparing for. But this is just to give you an insight, to make you understand certain things. And I'll be telling you whenever I make a video which may not be really important from the point of view of the exam, but may seem interesting to learn, to understand as to why we are doing something. So with that, this is Kalyan Kumar signing off. Have a wonderful day. Goodbye and thank you for watching.